Okay, so today we're going deep on some pretty mind-bending stuff, actually.
Yeah, I'd agree with that.
Yeah, we're really diving into the intersection of consciousness and quantum mechanics and information theory,
Mm,
which are three pretty huge topics in and of themselves.
right. Yeah, that's a hefty intersection.
Yeah, as always, I think our mission is to extract what are the really core ideas here, and in this case, we're really talking about how our perception of reality, maybe, and maybe the nature of mind itself,
Mm.
how all that might be understood through this lens.
Yeah, and there's a lot to look at there, and how those things connect. And the sources you've given me really hit on some of those connections.
Yeah, and the big question in this whole discussion in this whole area is what's sometimes called the hard problem of consciousness,
Yeah,
which is really just how does a physical brain, give rise to the feeling of subjective experience?
yeah.
And that question is kind of hanging over everything we're talking about.
It is. It's the open question that really kind of this deep dive touches on.
Right. And that is that's the crux of the matter, right?
Yes.
And one of the first things that pops up in this paper is this idea of the third state, which is offered as a kind of bridge between basic data and meaningful information.
It is.
So maybe we should unpack that a little bit. What exactly is the third state, and why is it so crucial here?
Well, what's fascinating here is the paper suggests that the third state is basically space itself, so not like empty nothingness,
Right.
but a fundamental component that exists between the bits of data that we think about.
Mm,
So it's kind of like the spaces between words in a sentence. I mean, if you think about it, if you take all the spaces out of a sentence, all the letters just run together, and you can't read it, you can't tell what it's saying.
right.
So the third state or space kind of acts in that same way for data. It provides that context and separation that's needed for patterns to emerge.
I see. So it's not just the ones and zeros. It's what's between them that helps to make them meaningful.
Yep.
It's like the silence between notes in music, which are just as important as the notes themselves for
Yeah.
creating the rhythm and the melody.
That's a really good analogy, and it extends even further than that. The paper suggests something really profound, which is that physical reality itself
Mm.
might be constructed from these incredibly basic units of data, like bits, matter, antimatter, or maybe even something or nothing, and that this third state, this space, as you put it, is the key ingredient that makes it all possible.
But wait a minute. How can something that seems like nothing be so essential for creating everything?
Well, if you think about it in terms of the grand scale of the cosmos, in terms of quantum cosmology, the idea is that at the most basic level, reality might be granular,
Okay.
made up of these tiny fundamental bits. And the third state acts as this universal separator. It provides the context that allows those bits to interact and organize themselves into the matter and energy that we perceive.
Okay.
So you can think about it like a grid, that the empty space in a grid defines where the lines can go to create a pattern.
I see.
So in a sense, the third state could be the very fabric upon which our reality is constructed.
Wow. So this is really a huge concept.
It is.
And finally, the intro touches on how consciousness in this very moment is like a snapshot.
Yeah.
It's a blend of our physical state, how we interpret our past, our predictions about the future based on the patterns we've seen and all the sensory information that's flooding in right now. And somehow all of this is connected to these underlying quantum processes in the universe.
Right. It's like we're at the center of all these different intersecting layers all happening at the same time.
It's a lot to think about.
It's like a multidimensional tapestry.
Okay, well, let's dive deeper into some of the specific discussion points here.
Okay.
And the first one that really stood out to me was this conundrum, the fact that our brains are, physically finite systems with limited capacity for storing information,
Right.
and yet it feels like we can remember so much.
It does feel that way, and it raises a really interesting question.
Yeah.
How can a brain, which is ultimately just a collection of cells with a finite number of connections, appear to hold and recall such a vast amount of information? I mean, think about all your memories, all your experiences, even your imagination. It seems almost limitless.
Yeah, it feels like we should have hit our storage limit decades ago.
Yeah, it does feel that way.
But we can still pull up childhood memories. We can
Yeah.
imagine entire fantasy worlds. it feels boundless.
It really does. And it's a challenge for classical information theory.
Right.
Because we know that to reliably store and retrieve information, you need some level of redundancy. You need clear separation between the data. So how can a limited brain afford all that extra baggage?
Right. It's almost like it's cheating.
Yeah, it is. It feels that way.
Now, the paper introduces this idea of quantum probabilistic compression
It does.
as a possible way to get around this apparent limitation.
Yeah.
And it's pretty mind-bending.
It is. It's a departure from classical thinking.
Yeah, so how does this quantum compression actually work?
Well, the key idea here is that no matter how clever our classical compression methods get, they're ultimately limited by the laws of information theory.
Okay.
If you have a finite storage space
Right.
and a seemingly infinite amount of data to store it, you're eventually going to run into problems. So this leads to the idea that maybe the brain is doing something different, something that goes beyond classical compression. And maybe it's using a form of quantum compression.
Okay.
Where instead of storing every piece of information as a separate distinct file,
Right.
it's more like storing a range of possibilities.
Right.
And then the act of remembering is like selecting one specific possibility from that range.
So it's not like having a folder on our computer for every birthday party memory.
Right.
It's more like our brain stores a fuzzy cloud of birthday-related data.
Right.
And then when we try to remember a specific party, that cloud collapses into a concrete memory.
That's a really good way to put it. It's kind of like the idea of wave function collapse.
Right, that I've heard about in quantum physics.
Exactly. So quantum probabilistic compression suggests that information isn't stored in a fixed binary way, but rather as this spectrum of probabilities. And that allows for a much denser way of packing information. So our finite brains could potentially access a much larger reservoir of memories and ideas than we might think.
So it's like we're using the uncertainty of quantum mechanics to our advantage.
In a way, yes.
Okay, now let's move on to this concept of the quantum brain.
Okay.
This is definitely a hot topic. There's a lot of debate surrounding the idea that our brains might be using quantum mechanics in some fundamental way.
It's definitely a controversial area, and the phrase quantum consciousness tends to evoke some strong reactions from people.
Yeah, can imagine.
But this paper takes a more grounded approach and suggests that maybe we can all at least agree on this basic principle that the brain is affected by the quantum realm.
Right, and it lays out a couple of pretty clear arguments for this, right? The first being that brain function is, it fundamentally relies on electrical signals.
Right.
And what are electrical signals made of?
Well, at the most basic level, they're the flow of electrons.
Right.
And the flow of electrons is a quantum mechanical process.
Right.
So even if you don't buy into the idea of the brain as a quantum computer, you have to admit that at the very least, at a very fundamental level, the brain's operation has quantum roots.
Right. It's not just chemistry going on. It's the movement of these tiny quantum particles.
Exactly.
And the second argument is maybe even more direct.
Yeah.
External quantum processes can demonstrably affect the brain.
They can.
And we're not just talking about subtle influences here.
No, we're talking about clear, observable effects.
Right.
I mean, think about getting an X-ray.
Right.
That's a form of electromagnetic radiation, a quantum prox. Right.
And when your brain is exposed to those high-energy X-rays, it can have some tangible and sometimes damaging effects.
Right.
So this shows quite clearly that the brain isn't isolated from the quantum world.
Right.
It interacts with it.
Right.
Whether we like it or not.
So quantum mechanics has a seat at the table, at least when it comes to brain function.
It does.
But the paper makes a really important point here that just because the brain is affected by quantum processes, that doesn't automatically mean it's a quantum computer.
Right.
That's a much stronger claim, right?
It is. And it's important to distinguish those two ideas.
Right.
I mean, there's no doubt that quantum effects are present in the brain.
Okay.
But the idea that the brain is actually using those effects for computation in the way that a theoretical quantum computer would is a separate idea.
Okay.
And one that's still very much up for debate.
Okay, so quantum mechanics is involved, but maybe not running the whole show in the way that some of the popular theories might suggest.
Okay, now let's zoom out a little bit here.
Okay.
To a cosmic scale and talk about this idea of the quantum cosmos.
Okay.
Why is understanding the quantum nature of the universe even relevant to understanding something as, seemingly personal as consciousness?
Well, because quantum mechanics isn't just a bunch of strange rules that apply to the microscopic world, the world of atoms and particles.
Okay.
Quantum cosmology is the field of physics that attempts to unify Einstein's theory of relativity, which describes the large-scale structure of the universe, gravity, galaxies, black holes,
Yes.
with quantum mechanics.
Okay.
And if we want to have a truly unified picture of reality, we need to understand how those two fundamental frameworks fit together.
Okay.
You can't have one without the other.
Right. So the big question here is the cosmos quantum?
Yeah.
Is the universe at its most basic level governed by these same weird quantum rules?
That's the question.
And the paper makes a pretty bold statement here.
It does.
It says the amount of resources, brain power research that we've dedicated to fields like astrophysics, particle physics, cosmology, basically answer that question with a yes.
Right.
Our best models of the universe, our most fundamental models, are all deeply rooted in quantum principles.
They are, and we're constantly discovering more and more about the quantum nature of space and time and the very origins of the universe.
So it really does seem like the universe itself operates on these quantum principles.
It does.
So if our brains are influenced by quantum mechanics and the cosmos is also fundamentally quantum count, then this field of quantum cosmology, this attempt to understand the quantum universe, might hold the key to a unified understanding of information at all scales, from the tiniest particle to our thoughts.
Right. It's all connected.
Yeah, this is all pointing towards a pretty interconnected picture of reality.
It is.
Okay, let's circle back now to some of the basic building blocks here.
Yeah.
This idea of data information and the third state.
Okay.
We've touched on the third state as being akin to space.
Right.
But let's really nail down what we mean by data and information first, as the paper defines them.
Okay, well, the paper defines data as the smallest, most basic unit of observation that we can currently discern. So think about it like a single binary bit in a computer,
Okay.
A1 or a 0.
Right.
On its own, it doesn't tell you very much.
Right.
Information is when you take a collection of that raw data and it forms a pattern
Okay.
that conveys something more than just the individual bits.
Okay.
So like the sequence 1, 0, 0, 10.
Right.
That pattern of ones and zeros can represent a number or a code, something meaningful.
Okay. So far so good. That seems pretty straightforward. But then the paper gives this interesting example
It does.
of how simply stringing data together can actually lead to a loss of information.
Right.
They use the example of taking two separate sequences of 10, 101 and just stick them together to get 10101 and 101.
Right.
And the original meaning that there were two distinct sets of data is lost.
It is, and that's where the third state, this idea of space, comes back in as really crucial. The paper argues that simply concatenating data, while it preserves the individual bits, it can obscure the intended meaning.
Right.
What's missing is that space, that third state,
Okay.
that acts as a separator
Right.
and provides that context to distinguish between the separate pieces of information. So if you have 1101 and then a space and then 1101,
Right.
that clearly conveys two distinct instances of the same data.
Right.
But when you remove the space and you just have 10101, 10101, it becomes a single longer string. And you've lost the information that it was originally two separate units.
So this space isn't just nothing. It's actively contributing to how we interpret data.
It is. It's like the punctuation in our sentences.
Right.
That tells us where one idea ends and another begins.
Right. So it's like the ultimate punctuation mark.
It's punctuation for the universe.
For the universe.
Yeah.
And the paper emphasizes that this concept of space as this meaningful separator isn't just limited to computer code or even language.
Right.
It seems to be a fundamental aspect of how information is structured at all scales of reality.
It does, and it's not just a human construct.
Okay.
It seems to be this fundamental principle operating across all domains, from the vast distances between galaxies down to the spaces between atoms, and even potentially at the most fundamental subquantum level.
Wow. Okay, now this next section really challenges a kind of a common belief, I think, that we hold this idea of considering the past.
It does.
We tend to think that knowing our past is essential for understanding who we are now and for predicting what might happen in the future.
Right. It's a very intuitive idea.
Yeah, but the paper seems to be arguing against that, or at least presenting a very different perspective.
It is. It's pushing back on that conventional wisdom.
And how does it do that?
Well, it uses a thought experiment about predicting past and future weather. based on a very small sliver of recent data.
Hmm.
So the idea is if you only knew the weather conditions for the last second,
Okay.
could you accurately predict what the weather was like a week ago?
Probably not.
And then use that prediction to forecast the weather for today.
Right. As we all know intuitively, the further back you try to go, the less accurate those predictions are going to be.
Exactly. And the paper uses this to argue that the further back we go in time to predict the future or even the past, the more the entropy of that prediction increases.
Okay, now entropy is a pretty complex concept.
It is.
Maybe you could just give us a quick and dirty definition.
Sure, you can think of entropy as the natural tendency for things to become more random or disordered over time.
Oh.
So the further back in time you go, the more chaotic and uncertain things become.
I see. So it's like trying to put together a jigsaw puzzle where the pieces are constantly shifting and changing shape.
That's a good analogy.
Okay, so if the past doesn't exist in this kind of concrete, easily retrievable way, then what are we actually doing when we remember something?
Right.
The paper has a pretty interesting idea here.
It does.
It suggests that our memories might be more like probabilities than fixed recordings.
Yeah, it's a radical departure from the traditional view of memory.
Hmm.
So the idea is that the past isn't stored in our brains like a video that we can just replay.
Hmm.
Instead, it's stored as this vast set of quantum probabilities
Okay.
that are somehow compressed within the finite structure of our minds.
Okay.
And then when we remember something, it's not like retrieving a file from a hard drive.
Okay.
It's more like a process where our current brain state interacts with those probabilistic representations.
Hmm.
And a particular version of the past, a likely configuration, kind of collapses into our conscious awareness.
So it's not a perfect replay.
No.
It's a reconstruction based on probabilities.
Yeah, it's like our brain is constantly generating a narrative of the past
Yep.
based on the most likely scenarios.
Interesting. And there's even a mention of a 2015 experiment
It serves.
by Van de Bogart and Forshaw
Mhm.
that seems to support this idea
Right.
that memories are stored in these finite probabilistic states
Yeah.
and that they might even be influenced or retrieved by some kind of remote quantum field.
Yeah, it's a very cutting edge idea.
Yeah, that's pretty far out there.
It is, but it's an area of active research.
Okay, so the past isn't a fixed book that we can open and read.
Right.
It's more like this probabilistic field that our present interacts with to create what we perceive as memories.
Yeah, it's constantly being rewritten and reinterpreted.
Okay, let's move on to this term fixed unity magnitude,
Okay.
um,
Yeah.
which the paper introduces as something more useful than just scale when we're talking about things in the quantum realm.
Right.
Now, why is simply talking about scale, big or small, not enough?
Well, because in quantum mechanics, the idea of scale is a little bit more nuanced
Right.
than just saying something is big or small.
Mhm.
Because in the quantum world, the act of observing something actually changes the thing that you're observing.
Okay.
So what we see is actually influenced by how we're looking at it.
Okay.
So using scale alone can lead to some paradoxes and even infinities in our calculations.
Okay.
So the paper suggests that this idea of unity magnitude is a more comprehensive way of thinking about scale in a quantum context.
Okay. So it's like a quantum scale.
Yeah, in a way it is.
Okay.
It's a measure that describes the overall size or capacity of a system's phase space, which is basically the range of all possible states that a system can be in.
Okay.
And it takes into account the limitations and capabilities of the observer.
Yeah.
So it's not just about how big or small something is, but how much information we can actually gather about it.
Okay. So how does this help us to make sense of how a finite brain can handle seemingly infinite amounts of information?
Well, by sampling the sensory data that we receive
Oh.
with a fixed unity magnitude, the brain can essentially synchronize information to a stable internal clock
Okay.
that's independent of the fluctuations of space-time.
Okay.
And that allows it to keep the overall quantum probabilistic state of our understanding within manageable limits.
I see. So it's like we have this consistent window
Yeah.
through which we perceive and process information,
Hmm.
regardless of how much data is actually out there.
Right. It's like having a built-in filter.
Okay. And the paper gives an analogy about adjusting our physical distance to see a distant object more clearly,
Right.
which is kind of like adjusting our
It is. It's about finding the right level of zoom
Right.
to make sense of the information.
Okay, and it even points to biological examples, like the way the ribosome in our cells decodes our DNA
Right.
in fixed steps of base pairs,
Right.
which suggests that maybe there are these natural biological scales of unity magnitude
There might be.
at play even in very fundamental biological processes.
Right.
Okay, so this idea of a scale of observance that leads to this really interesting analogy of the not so thin blue line, our Earth's atmosphere,
Right.
which is something that seems pretty simple from a distance,
Yeah.
but reveals incredible complexity when you get closer.
It does, and that analogy shows how the number of observable details changes drastically depending on your scale of observation.
Right.
I mean, from space, the Earth's atmosphere looks like a very thin blue line,
Right.
but as you zoom in, that line resolves into a multitude of distinct layers, each with their own characteristics and processes. And this is similar to what mathematicians like Helge von Koch have found with fractals,
Oh, okay.
which are these infinitely complex patterns that can arise within finite spaces, simply by changing the scale at which you examine them.
Right. So what seems finite and simple at one scale can actually be infinitely complex at another scale. And the paper shows this really nicely in Figure 1, where it shows a single abstract character being viewed at different scales,
Right.
macro, micro, and even quantum.
Right.
And it really drives home this point that the scale at which we observe something fundamentally dictates what we see as distinct elements.
It does. It shows that our perception of reality is not objective
Right.
and fixed.
It's tied to the scale at which we're observing.
Exactly.
Okay, so the paper then tackles this question that might seem kind of obvious at first. Can a finite data state space generate all information that might exist?
Right.
And the answer, as it turns out, is yes, at least in principle.
Yeah, it's a deceptively simple question.
Right.
But it has some profound implications
Yeah.
because it means that even if the underlying structure of reality is finite, it doesn't necessarily limit the amount or complexity of information that can be generated from it.
So how does that work?
Yeah.
How can something finite produce something that seems infinite?
Well, think about a computer. All the complex data that it processes,
Right.
text, images, videos, it's all ultimately represented by just ones and zeros, a finite set of states.
Right.
So finiteness in the underlying data doesn't necessarily mean that you can't represent infinite complexity.
Okay, but the paper adds a really important caveat here.
It does.
And it brings us back to the quantum realm.
It does.
It says that not every possible configuration of a compressed phase space. Now, a phase space is basically the range of all possible states a system can be in.
Right.
So the paper says not every configuration of a compressed phase space can actually exist distinctly as an uncollapsed wave function.
Right.
And now, just to clarify for our listeners, a wave function in quantum mechanics is basically this probability distribution of all the possible states that a quantum system can be in before we observe it.
Exactly.
So what's the paper saying here?
Well, it's saying that while a finite space of data states could theoretically represent any information, the principles of quantum information theory tell us that not all of those theoretical representations can actually manifest as stable, observable states. So some quantized states will inherently have the same probability of representing multiple different final observations. So before an observation is made, the system exists in a superposition of all those possibilities. But once an observation is made, it collapses into a single definite state.
Okay, so even with a finite underlying structure, this quantum nature introduces a level of uncertainty.
It does.
About what state will actually be observed.
Yeah, it's like rolling a dice.
Okay.
You know, you have a finite number of sides, but you don't know which side will land face up until you roll it.
Okay, now this leads to a really interesting point about errors and creativity.
It does.
Now, in classical information theory, if compressing data leads to errors or loss of accuracy, that's generally seen as a bad thing for memory.
Right.
Right. We want our computers to store information perfectly. But the paper drawing on Forshaw's work from 2015 suggests that these potential errors in our brains, probabilistic memory, might actually be beneficial.
They might.
So how could that be? How could errors be a good thing?
Well, the idea is that these errors aren't just random noise.
Okay.
They might actually be a fundamental source of new information and even creativity.
Right.
So when a memory is stored probabilistically and recalled,
Hmm.
The act of recall forces it to collapse into a specific state.
Right.
But if that collapse isn't always perfectly identical to the original encoding,
Right.
and there's some slight variations or errors,
Right.
then when this slightly altered memory is recompressed,
Hmm.
it can potentially lead to the recovery of entirely new information
Hmm.
or novel combinations of existing information that weren't explicitly stored before.
So it's almost like a form of quantum brainstorming.
Yeah, in a way it is.
Okay, so these mistakes in recall
Mm-hmm.
aren't just a sign of an imperfect memory.
Right.
They might actually be the seeds of new ideas,
They might be.
new connections, and ultimately imagination.
Yeah, and the paper even suggests that imagination and creativity might cease altogether. If a system's configuration was completely and perfectly mapped, without any room for these probabilistic variations,
So you're saying we need a little bit of imperfection
we might
to be truly
a
creative.
little bit of randomness.
Okay, now the paper uses this example of the Mandelbrot set program
It does.
as a really clever illustration of this process of how data becomes information.
Yeah, it's a beautiful example.
Now, for those who aren't familiar, the Mandelbrot set is this incredibly complex and beautiful fractal
It is.
that's generated by a really simple mathematical formula.
Yeah, a very simple formula that's applied iteratively over and over again.
Okay, so how does that relate to data becoming information?
Well, the Mandelbrot set program takes a very basic set of rules and applies them repeatedly. The output of one calculation becomes the input for the next. And even though those initial rules are simple, and you're starting with what could be considered almost random data, this iterative feedback process leads to the emergence of incredibly complex self-replicating patterns. So it shows how structure and meaning can arise from repeated interaction, even from seemingly random beginnings.
So it's like order emerging out of chaos.
In a way, it is.
Okay, and then the paper takes this idea even further.
It does?
And it broadens our definition of what a computer is
Right.
beyond, just the devices that we have on our desks.
Right.
It suggests that any mechanism that moves data around can be considered a form of computation.
Yeah, it's a very broad definition.
Yeah.
Yeah.
So what are some examples of that?
Well, it could be natural systems like the wind or the sun or even the entire universe itself.
Right.
If we think of data as the most fundamental constituents of reality, then any system that causes those elements to interact and change, right,
is performing a kind of computation.
Okay, so the universe itself is a giant data processor.
Yeah, that's the idea.
Okay, this brings us to this concept of frequency as primordial data.
It does.
Now, the paper argues that frequency, this idea of cycles and vibrations, was perhaps the very first form of information to manifest in the universe.
Yeah, it's a very interesting idea.
Yeah.
So in the very early universe, in the moments after the Big Bang, there would have been countless collisions of particles.
Right.
And those collisions would have created vibrations and oscillations at different frequencies.
Okay.
So you can imagine this primordial universe as a cacophony of frequencies, a kind of fundamental data set from which all subsequent information arose.
And the paper even mentions Mei-Wanho's work.
It does.
On the electric plasma universe and galaxy formation.
Yeah.
As an example of how these cosmic scale interactions can lead to structure.
Exactly. It's a beautiful example. Okay, so if we think of the universe's ongoing motion and interactions as the computer,
Right.
and these elementary frequencies as the initial bits of data, then the same fundamental rules of information theory should apply throughout the entire history of the cosmos.
Yeah, it's all one big interconnected system.
Right. So how did we get from this primordial soup of frequencies to the complex structures that we see today?
Well, over vast stretches of time, those initial frequencies.